Hello everyone, in this lesson we will explore modeling with exponential and logarithmic functions. Just note that algebra still matters, it's very important. Given some equations, you identify a variable in which you want to solve for, get that variable to one side of the equation. Whatever you do to the left side of the equation, you must also do to the right side. Also, we'll be using opposite and inverse operations pretty frequently. For example, addition and subtraction, multiplication and division, squared and square roots also come in handy. E to the x and ln of x, these are some. We recall an exponential growth diagram. Exponential growth diagrams, they're rising from the left to right and they're going up pretty quickly. So this is exponential growth. There's a diagram of exponential growth. Then there's also exponential decay diagram. An exponential decay diagram, that is one that falls, right, as we go from left to right. So exponential decay falls as we go from left to right, okay? Now we will explore another kind of growth diagram, which is a logistic growth. And in this case, our model will be it is rising as we're going from left to right. And then it approaches like an asymptote and flattens. So it rises and then flattens. There's a point of inflection in the middle of the curve. As you notice, first it's increasing the rate of change and then decreasing, unlike the exponential growth model, which just keeps on increasing. We use the form y is equal to c over a times e to the negative bt, where a, b, and c are positive constants. The line y equals c is a horizontal asymptote of the graph. That means it's a limiting value. It's the value that the function will not go beyond. Okay? You look at similarities and differences between the kind of models, exponential growth and logistic growth, they both rise. Whereas for exponential decay, it's falling, right? Or flattening out to an asymptote at 0. Exponential growth flattens out to an asymptote at c at the top. Okay. Let's look at a couple of examples of working through some problems in this section. First question, given p is equal to 100 e to the kx minus 100, solve for x. So we want to solve for x, and x is up in the exponent. So p is equal to 100 e to the kx minus 100, and I want to solve for x, okay? So let's do a bit of algebra on this. First, we plus 100 to both sides. So on this side, we have p plus 100 equals 100 e to the kx. Then we divide both sides by 100. So we have p plus 100 over 100 equals e to the kx. Next, you want to apply an inverse operation, ln to both sides. Apply ln to both sides. We get ln is equal to ln of that. Now, ln is the inverse operation of e, so it will undo e. So that means ln of p plus 100 over 100 equals k times x. And finally, to get x by itself, we divide both sides by k. Both sides by k. So now we'll have x by itself here. So x be equal to ln of p plus 100 over 100 divided by k. That is our final answer for that problem. Problem number 2, you had s is equal to 90 minus 20 ln of t plus 1, and we want to solve for t. We want to solve for t, so we want to solve for this guy here. So we want to eventually isolate t. First off, let us subtract 90 from both sides. Let's subtract 90 both sides. What we'll have then is s minus 90 is equal to negative 20 ln of t plus 1. Then we want to divide by negative 20, because we are multiplying by negative 20 here, so divide by negative 20. And so what we have then is s minus 90 over negative 20 is equal to ln of t plus 1. Because we have an ln of t plus 1, here we want to apply the inverse operation, so we apply e to both sides, or exponentiate both sides. If we exponentiate both sides, we'll have e raised to this side equals e raised to the next side. Okay. Now notice e and ln are inverse operations. So then it becomes e to the s minus 90 over negative 20 equals t plus 1. All right. And finally, to undo this plus 1, we subtract 1 both sides. So final answer will be t equals e to the s minus 90 over negative 20 minus 1. That is our final answer, and we're done. Okay. Let's look at some other applications of logarithmic and exponential functions. So this question says, on January 1, 2000, the population of California was approximately 34 million. On January 1, 2010, that's 10 years later, the population was 37.3 million. A, write a function of the form p of t is equal to p0 ex e to the kt to represent the population of California t years after January 1 and round k to 5 decimal places. Part B, use a function in part A to predict the population in January 1, 2018. That's 18 years later. So let's start by writing the function that we want, p sub 0 e to the kt, right? That is equal to p of t. Okay, that's the remaining population. P sub 0 is the initial population. Okay, so the initial population then would be 34 million. So that is our P sub 0. Right? The remaining population, or the final population, was, we want to call it P of T, which is in the year 2010. Well, let's just plug in this for P of T. What else do we have? That's pretty much it, so let's plug in. So 37.3 is equal to 34 e to the kt. And then we're trying to find k first of all. So t then would be 10 years. We said that t was 10 years from 2000 to 2010. So let's write that in as well. T is equal to 10 years. So let's plug in our t here at 10. So then now we only have one variable to solve for, which is our k. Alrighty, so divide both sides by 34. Divide by 34, both sides. And so what we're left with is 37.3 over 34 is equal to e to the 10k. Right. It's multiplication, so we can interchange them. Then we apply ln to both sides. So we apply ln. So we take ln off this side. And ln of the other side. The ln will undo the e, so we take ln on both sides. Ln here is the inverse of e, so that those undo each other. So what we have left is ln of 37.3 over 34 equals 10k. And finally, we can divide both sides by 10 to get our value for k. Divide by 10, divide by 10. So we have k equals ln of 37.3 over 34 all over 10. And if we plug that into our calculator, we'll get approximately 0.00926. And so that is the k that we will be using in our formula. So formula then will be P of T is equal to 34 e to the 0.00926 t. So that is our formula. Then we will use this to find the population in 2018. So we're using P of T now is equal to 34 e to the 0.00926 t to be 18 years, 18 years after 2000. And so we get 40.2. We know that is in million. So that will be our population in 2018.